Hello everyone, are you able to hear me clearly? Alright, so I'm assuming that everybody is able to hear clearly. Okay, so today we are going to continue from where we left last time. Alright, okay, so last time we discussed we discussed various strategies to do a very simple problem like sorting. Okay, in this, the way we discussed the problem was that we we tried to solve a problem of counting words because counting words involved sorting. So so we first tried to do it in a normal programmatic way. Then we used SQL, then Unix with a sort command which tries to do things in the disk rather than in the memory. And then we compared all these approaches. Afterwards we came up with another approach, the fourth one, where we were using multiple machines. And then we talked about what are the problems with external sort. Then we ended with that the problem with the external sort was mainly the transport of data, and for each requirement, you have to stitch a new program. So, how does MapReduce solves that kind of problem? Okay, so a brief introduction of MapReduce again. So, MapReduce is basically a programming paradigm. It helps you solve big data problem, specifically sorting intensive jobs. And you generally have to write two functions. One is called mapper and other is called reducer. The mapper function, this is the code you will write. So if you are writing MapReduce code, mapper function converts input into key value pairs, and reducer function aggregates all the values for a key, and in between mapper and reducer the data passes through map reduce of Hadoop. So okay, we'll go into details again. And map reduce is not only specific to Hadoop anymore. It started with Hadoop. It started with Google writing a paper called MapReduce, and after that, the same thing has been adopted by MongoDB, Cassandra, and CouchDB, and few more. And even the newer frameworks like Apache Spark uses MapReduce kind of paradigm. It's not exactly like the MapReduce we are discussing, but it does have the same functions with a little different name. Then mapper and reducers can be written in Java, Shell, Python, or any binary you can use as MapReduce. All right. So this is like a theoretical overview. Let's get into the details. Now, all right. So let's first focus on these two boxes. What do these two boxes do? And then we analyze how would a MapReduce framework in general do. As we just told that a map function takes an input and it converts it into key value pairs. Here, our map function is converting a single line of text into one word per line, and each line contains key and value. The key here is word, and value here is numeric 1. Now, that is our map function. Map function is breaking down our our input line into key value pairs. All right. And why is it doing so? Because Hadoop will take the output of map function. Hadoop will take the output of map function and then it will group by the key. For example, so again, let me take a step back. As part of MapReduce in Hadoop, what does Hadoop do? So we tell Hadoop that we want to process certain data. We tell the file name of the file which is lying in our HDFS. Okay, we put we give the URL of the file which is lying in the HDFS to MapReduce along with along with our function called map function. So what will Hadoop do with the map function? Hadoop will pick up the file which we want to process, read one line at a time, and against that one line, it will execute the map function. Now, for each of the lines in your input file, your map function is getting executed, and your map function is supposed to give key value pair. So, whatever key value pair your map function returns or map function gives out, Hadoop takes all of them and then it sorted the output. So the output of your map function is gathered by Hadoop, which is like key and values. Now, Hadoop will take all those key value pairs and sort them by the key, and after sorting them by the key and grouping them by the key, your result will look like this. It'll be GA1, RA1. This is just an example. So you can see that there was, let's say, one line, sa, re, saga in our input. There could be hundreds of such lines. For each of these of those 100 lines, a similar output will be generated. All right. So and this dashed line here, this dashed line is the job of Hadoop. Okay, this dashed line is job of Hadoop, and uh, because as we earlier told that Hadoop is nothing but a grand sorting machine. Sorting as in it sorts the data, whatever data you give it to Hadoop, it sorts it and groups it. Okay, so and that's the reason why we are giving, as part of map, we are giving out key value pairs. Okay. We are telling Hadoop that please sort our data by this key. All right. And once the data is sorted, if you want to do a post processing of each key value pair, you can write a function called reduce and tell the by launching the job of map, we can tell Hadoop that this is my reduce function and it whatever values it receives for each key, it will do something. And in this case, in this example, it's going to do the summation of all the values for each key, which means the reduce function is going to be called once for each key, while our map function is going to be called once for each line. All right. So Leonid's question is, does reduce function happen on data node or name node? Okay. So I'll explain to you this one again in a minute. All right. So I'll like to explain the first then this part and then I'll take the question. All right. Now I'm taking a step back again. So what exactly are we doing here? In case we are telling Hadoop that, hey, this is my data. I want to I want to do kind of a group by on my data. Group by, you understand? There's a group by function in SQL where we tell that group by this column and once all the values are grouped by this column, we will aggregate them in this fashion. So that's a SQL command of group by. So in the similar fashion, we are here trying to do a grand group by using Hadoop. Okay, so the MapReduce paradigm is all about getting your data grouped by a certain key, and then for each group of the data we can apply reduce function. Okay, so so essentially your problem will boil down to the fact that how would you convert your problem into a group by problem, or how would you convert your problem into a sorting problem? All right, now brief again recap. So whenever we are saying that we are scheduling our MapReduce job on Hadoop, we give Hadoop the input file. We tell Hadoop that this is going to be our input file. Second, this is going to be our function, and this is going to be our reduce function. Okay, unlike in a traditional case where our program directly reads file, here we are handing over the file to Hadoop, and then we are telling that for each line of this file which we are giving to you, please execute our map function, and whatever is the result of our map function, please sort it by the key which we will be specifying. And once you have, we are telling Hadoop that this is my reduce function, please execute this reduce function on each key in this input. All right, so now Leonid's question: does reduce function happen on data node or name node? So okay, so here the question is that, first let me explain quickly, and then we'll again anyway come back to the question. So we the important part here, the way we have described just now, that our map function will be executed for each line of the data. That means that it will be possible, and that's what Hadoop will do. Hadoop will take your map function and will execute it near to the data, wherever is this data lying. Okay, wherever this data is lying, it will try to execute it near that. If you have 10 nodes and this file is spread over 10 nodes, and these files contain the blocks of data. For each block of data, your map function is going to get executed per line. All right, now question occurs that once map function get executed near the data node, as in when we say near the data node, so almost on all the data nodes we run the task tracker, and we basically try to find out that where is the task tracker, and we try to execute map function. I mean, Hadoop tries to, not we. Hadoop tries to do all of that. So we try to execute this map function closer to the data. Now, question arises that if map function is being executed near the data, then where is reduce function executed? Okay, reduce function is executed on any of the the task trackers which are closer to all the task trackers that are running on these mappers. Okay, so the node which is closest to all, you will see that because the map is going to be run on multiple machines, and reduce is generally run on a different machine where the data will be gathered and shuffled. Okay, so generally the reduce function is executed on a different node. All right, but not at all on or name node or job job tracker. Okay, it's just another task which gets executed. All right. So, yes, Leonid, it might get executed on any of the task trackers, or you can say the data nodes, or it might, I mean, it will be executed on any of the task trackers, which is closer to the data. All right. Now, Weber's question is, so reduce function will be on one of the many task trackers. So yes. So, yes, Weber, that's correct. Reduce function will be on one of the many task trackers which are in the near vicinities of all the mappers that are getting executed. So Matthew's question is, can the data be partially reduced before sending it to the machine doing the reduce? Yes. It can be partially reduced on the same node as the mapper, this mapper node on which map function get executed before doing before doing the uh, transfer of the data. All right, we call them combiner. You will see that very quickly. Very good set of questions. All right, all right. Now we have Kiran's question. Suppose we have 10 different files in HDFS and we want to execute MapReduce program for one of the files. How Hadoop recognize that MapReduce program to run for which file? For example, I have a word count related file called world temperature file, and my MapReduce program is let me just copy it here so that everybody will be able to. Yeah. All right. Suppose we have okay. So in a very simple words, Kiran, whenever we are starting our job, whenever we start our MapReduce job, we would specify to Hadoop that hey, this is my input file, this is my input file, this is my map function, this is my reduce function. We that's as part of the whole program. Okay, you will get to see that. No worries. All right. So Weber is saying, will there be multiple reducers or just one reducers? Yes, there'll be multiple reducers. I think the time has come to move to the next screen. All right. So let me further let me go a little step further. All right. Now in the previous screen, what we did was we had only one node and we tried to compute the word count. So here what we have done is we had this line sa re saga. Imagine that there is a big file containing such lines, many such lines. So for each line is going to be broken down into key value pairs. Okay, and the resulting data will be like this. And after this key value has been generated, Hadoop has sorted it, and then it has passed each key value via our reduce function. It has passed our each key value through our reduce function, and we have got and our reduce function has summed up all the values for each key. Okay, that's how we got a nice word count problem solved via map and reduce. All right, we will see many more examples of very different kind of problems, how to solve them using MapReduce. This is just word count. All right, we'll have one of the toughest problems which we will try to solve. All right, next is that imagine that our data is on two different nodes. Our data is on two different nodes. node 1 and node 2. Node 1 contains sar a saga while node 2 contains sar a sa. Now what happens is node 1 will be again executing the same MapReduce function, and node 2 will again execute our same MapReduce function. So you can see that Sare Saga became Savan, Raven, Savan, and Gavan. That was done by our map function. Similarly, on the second node parallelly, our map function is being executed against the input data. And it becomes Savan, Raven, and Savan. Savan, Raven, Savan. For each word, we are forming key value pair. Alright. Now on this sorting will happen on both the nodes, here as well as here. So sorting will happen on both the nodes, and when the merging happens, now when the merging happens here, um, after merging, the grouping will happen. Okay, after merging, the grouping will happen, and we'll have our results in the form of the key and value again. And these results are found by passing our key and the value through the reducer. So key values came from node 1, key values came from node 2, both got sorted, then got merged. Then after getting merged, while merging itself, it took care of sorting. So you can also say it in another words, they got merged and sorted. All right, they got merged and sorted. Now after this, we got the formation of key and the values, and successfully each key and value got passed through reduce function converted the array of values into a single value, and here we have by reduce function basically summed up all the array of values, and we got this. Okay, all right. Now again back to the Leonid's question. I mean, I'm trying to repeat the question because that's a very important question to ask. Because Kiran also has the same question. On which on which node reduce function will be running? Okay, so if you understand that, so what Hadoop is trying to do, Hadoop is trying to minimize the transfer of data from node 1 to the node where map function gets executed. In our traditional programming, if you have done any J2E or other kind of database programming, our program fetches the data from the database server, does does some processing, and then saves it back to the database or presents it to the user. So in the traditional sense of programming, we generally used to transfer the data, and that was a part of our life. But when we discussed in the previous problem that transferring the data is a big problem, so let's execute our code on all the machines uh, near the data. Instead of transferring the data, we'll transfer the code, and that's what we have done just now. We gave only the map function, and Hadoop took it and executed on all the nodes. Whatever function we write, we have no control over we have no control over customizing that. On first node we will execute this function, and on the second node we'll execute some other. No, we don't have that control. Here we just say that this is my input data, we're going to execute our map function on that input data. All right, now uh, so we execute the Hadoop will execute our map function as closer to the data as possible. But as you can see here, the reduce function does a summarization. You need to get the data from all the nodes rather than one node. Therefore, it wouldn't make much of a sense to execute reduce function on either node 1 on node 2 or node 3. I mean, on any of the nodes on which the data is being done. Reason being, if you try to execute reduce function on node 1 or node 2, it will be an overhead on node 1 or node 2. We will not be able to execute reduce function by the time node 1 and node 2 have finished their work, right? Therefore, reduce might have to wait for node 1 and node 2 to finish, and only then it will work. If we try to execute reduce function on any of this. So therefore, keeping all of these things in mind, Hadoop checks that what is that node which is free in the network. Based on that based on that it executes reduce function closer to node 1 and node 2. All right. All right, this example is for only one reducer. Okay, before we move to further, I would like to explain one more thing. I'd like to explain one more thing, and then, all right, we have some more question before that. So Leonid is saying, since the node could have different, I think I'll let everybody read. Since the node could have different resources, Hadoop will decide what machine to execute based on available resources as well, not just the amount of data stored on the node. Perfect. That's exactly the reasoning. We Hadoop will find out which node is available for. I mean, that is the role of our job tracker or yarn to find out which machine is free and execute reduce on that machine. Brilliant. All right. So, Vaibhav, we are still discussing a single reducer. Now, there are a few more questions which people ask here. What is the point of sorting the data on each individual node? We know that the data at the end of day has to be sorted. But what's the point in sorting here as well as here, and then finally while merging we anyway have to sort it, right? Okay, so anyone can answer this question. So while merging we anyway have to sort our input data, as we have said that reduce will get the grouped keys, as in whatever key we have defined, reduce will get that key and all the values grouped together. Okay, to do that, it has to gather all the key values from all the nodes and then sort them and then group them. To group them effectively, sorting was the best technique. Okay, therefore, it tries to group them. Now, question is, why does it need to sort on node 1 or node 2 when it has to again merge and sort? All right, so we have. So, okay, Matthew says because if it is partially reduced, it will optimize the reduce if the machine has available resources. Brilliant, brilliant. Webber says faster since it doesn't have to wait for all mappers to finish. Um, it okay, so it doesn't have to. Okay, that's a good point. Let me note it down. Yes. So reduce doesn't have to wait for all the reducers to finish. To start the process of reducing. All right, it will save time. Yes. So basically, if you think about it, if this merge is happening on a single node, so that particular machine will be overly loaded. That particular machine will be overly loaded. Therefore, we have to distribute that work as much as possible. So Hadoop tries to get it executed on individual nodes, right? So with multiple nodes, we got multiple processing power, we got multiple IOs, and with the Hadoop kind of environment, we got the ability to execute our program near the disk. reducing the network transfers. Now, when we got multiple nodes running in parallel, it will make sense to utilize them rather than overloading the single node. All right. Now, question question still remains that how can partial sorting help in the overall merging? Okay. So I'll try to demonstrate to you that let's say you have two nodes, okay, node 1 and node 2. If the data in both of them is sorted, it's very easy to merge the data. Okay, it is easy to merge the sorted data. Okay, let's imagine that when I say easy, it means less CPU intensive. Okay, so let's say we have node 1, and node 1 looks like I mean node 1 looks like 2, 3, 6, 7, 8. So which means the data on node 1 is already sorted. Now let's say there is another node on which the data is sorted. Okay, if you have to merge these two data sets, one is this, other is this, to form a sorted result. So what will you do? Imagine that on first node these are the key, on second node these are the keys. Okay, if you have to merge these two sets, it's very easy. We basically compare the head, we compare these two, and and pick up the smallest one. So when we compare these two and we find out that one is smaller, so we put one in the output, remove one from here. Now again we compare the two and put the smaller one and remove that smaller one from the queue. And then we again compare these. And if they are equal, we just take both of them out and remove it from here. All right. Then again we remove 3. We compared it. Okay. And now out of these, which one is smaller? 6, and then 7 and 8. So this is, if you see, we did not have to go through these lists multiple times. We could just go through it once and solve our problem, all right, of merging. Therefore, it is just very straightforward and linear in nature. Linear in nature as in, if there are n number of records in both, the total time will be proportional to the total number of records, not square or not any other way. So it was very straightforward to merge two sorted lists. If these were not sorted, then it would require a lot of time on the node on which we are running here. We are running merge. It will take a lot of time on this node to do the sorting. And we have already told the sorting is probably the most intensive exercise in all of this process. Okay, sorting is CPU wise, sorting is CPU and RAM wise, sorting is the most intensive process. Therefore, as much as delegation possible, we do the sorting, and we are lucky to have this situation that sorting could be delegated, right, to individual nodes rather than having a situation where all the sorting outputs have to combine together. All right. Okay. Yes, thank you, Vaibhav. So it's like joining the two tables. That is correct, Vaibhav, because while joining the two tables, internally databases sort the two tables individually and then try to join them, because that way it becomes easier. All right. Okay, I'm happy, Kiran, that you like the explanation. So everybody's okay, right? That we have how we delegated the sorting work to each individual machines and how we solved the merging of sorted data. Yeah. All right. So everybody okay with the map reduce so far? If you have any questions, you can ask me right away. So the questions might arise things like, what should I keep as key? What should I keep as value? Okay. So the answer is the basis on which you want to group your data, or you want to bring, if you have a criteria that based on this criteria, I want to bring all the records together, then that criteria becomes your key. All right. And no matter which node that particular key exists, all of those values will be brought together. Okay. Okay. Now next, uh, I mean, so the strategy in all of the map reduce problems is that we try to form the keys in case of map such that our data comes together, and in the reduce function we combine the data for each key if needed. We are free not to combine also, but it is an added luxury. Okay. Now, coming back to the point again, that for a map reduce job, so far, what all input have we given? Anyone? What are the inputs we have given to our map reduce job so far? What is the input from your side? Anyone? What files to organize? Okay, that is Matthew. Number one is file. Okay, input files we call it. All right, that's also from Leonid. Okay, the map and reduce function, that is okay. Yes, map function, we call them separate. Map function, it's a function definition, and reduce function. All right. Okay. So Vaibhav's point is that input file and argument. Okay. So argument as in, okay, you're saying that input file as argument. Okay. And input data, that is great. Great. Now, there is one more thing which I missed here, that results of our work will get saved in HDFS. For that, you'll have to tell about output folder as well. Okay. So we give an input file, file or files, and we provide the map function as input, as the function which needs to be executed, and then reduce function, and then output folder. All right. Now we move forward. There are more things which we can specify, which we can tell to Hadoop, that those will come under further detailing. The next fifth argument is how many reduce function, how many reducers. Okay, that is the next thing which we want to discuss. Okay, so we can tell Hadoop that, hey, we want to run our reducer on multiple machines. We want to run our reducer on multiple machines because we realize that, okay, I think I missed a very important question from Kiran. His question was, do map functions should always be bigger than reduce function? Not necessarily. It all depends upon your business logic. All right. It all depends upon your business logic. All right. Now, in the input, we could also tell Hadoop that, hey, my reducers are getting very much load. Reducer node, single node is getting overloaded. Please do the job on multiple reducers. Okay. Now, no matter how many reducers are there before we go forward, a key and all of its values will always come to a single node. Okay. No matter how many reducers are there, all the keys, all the values for a key, no matter on which node does it exist, all will have to be brought on a single machine. Okay, so this is how it looks like. This phase called merge and shuffle, we'll look at it again. In this merge and shuffle, what happens is this sorted data gets merged and then splitted. This shuffling happens here such that some of the keys go to first reduce function, some of the keys go to second reduce node. First set of keys go to the first, some of the keys go to the one reducer node, some of the keys go to the second reducer node, and the only thing we need to remember is a key and all of its values are guaranteed to be on a single reducer node. It would never happen that some values for a key went here, some other values for the same key went to the second node. That will never happen at all. Okay, that is the sole idea behind MapReduce. Because a reduce function, as we told earlier, reduce function receives key and all of its values, no matter on which node these values came from. All right, now let's just go through the input data here. So, wow. All right, now here if you see, this is our input data, SAR saga. Let's imagine that there is one line on one node, another line on another node. Then on node 1, this data was fed to our map function. Our map function converted this data into key value like this Savan, Raven, Savan, and Gavan. For each word, it has split it. Here, this Sav is key and 1 is value. We could also put any other thing like X instead of 1 or something else. Just that the same thing need to be handled by our reduce function later on. And once here we have formed the keys, sorting will happen on local nodes, and then this black box called Hadoop will I mean, these three works, this work is being done by the Hadoop internally by merging them and then splitting them again into two parts. So if you can see that at this point, sa re re has gone to first node, and sa has sorry ga re re has gone to first node, and sa has gone to the second node. It would never happen that two sa have gone to first node and two sa have gone to the second node. Okay, otherwise we will never be able to count properly. Our job was to count the words here in this example. Had two sas gone to the first node and two sas remain on the second node, and when our reducer function was running here as well as here, we will get sa2 and sa2 in the results. Okay, so the reduce function's output goes to the HDFS. In this case, there will be two output files, one for each reducer. Okay. In our previous case, there was only one output file for the reducer. Here there will be two output file for the reducer. All right. Kiran's question is, where will merge and shuffle happen in Hadoop? In other unused data nodes? That's correct. Okay, that's correct. All right. So I'm trying to answer to Matthew's question as well. So the number of reduce, how many number of reducers do you want? We can specify while launching our job. So this these are the five inputs we are giving to Hadoop as of now. Input file, map function, reduce function, an output folder, and how many reducers. Okay? These are the five things we are feeding to our Hadoop. All right? Great. So any questions till now? All right. So Kiran's question is that what is the performance of merge shuffle if my file is 1 TB? The performance is actually very, very good. Okay. As I was telling you, the same framework, the exact same framework at Google could sort 10 petabyte of data using 8,000 nodes in around 6 hours. Okay. So it's that kind of performance we are talking. Now, Matthew's question is, isn't that dependent on how many machines the company has available? Very good point. Very good point. So your duty as when you're launching a job will be to decide how many reducers you can have. I'll help you in this understanding how to decide how many reducers. It should definitely do not should not go beyond a certain limit. Okay, because of the number of machines, of course. But yes, it's a very valid point that number of reducers is function of how many machines are there. Okay, and you will notice that number of reducers we will specify more than number of machines, and we'll explain it why. All right. So Webber's question is, does Hadoop decide the merge shuffle logic for reducers? Yes. Merge shuffle logic, the only input it takes is how to sort the data. Okay, that's the only input it is going to take, and rest of it will do it internally. O- Okay, so the question is then how many mappers are executed? As Kiran is saying that map functions are equal to number of splits of the file, that is correct. Okay, so if you have hundreds of hundreds of the input blocks, if you have 100 into 128 MB, which is around 12 GB, if you have those many blocks spread across your 100 nodes, then 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 basically there will be 100 map function being executed on 100 nodes parallelly. All right. So we generally do not control number of maps. We do not force Hadoop that these are the number of maps you have to have. But sometimes we can tell Hadoop that that even though our input file is very small, but still I want to execute. Even though our input file is very small, I want to execute map function parallelly on multiple nodes. Okay, so that is one thing. So still we can configure the map function. So I'll just make a note of it. And optionally, these are all optional. Okay. So this is also optional. So input file is kind of mandatory. Map function is kind of mandatory. This is also optional. Output folder is mandatory. And how many reducers is optional? How many mappers is absolutely optional. Okay. So we got 6 inputs so far. All right. So my voice breaking for all? Anindita is having an issue with the voice. All right, all right. For all, the voice is okay, Anandita. So all right. So I hope everybody is with me on how is this map and reduce happening. All right, Webhav. Okay, Leonid, Kirupa, and Kiran and John, Harsh and Deepak and Anandita. Are you all with me? So Harsh, my question was that is it clear the map reduce is clear to you? Great, great. All right, so everybody is with me. Now I'll try to represent the same thing for using a different diagram. Now you have this input HDFS file having 3 blocks, 1, 2, and 3. Okay. Each block is being passed through your map function, giving out the key and the values here, key and the value, key and the value. And then the sorting is happening on each node parallelly. Here, here, here. Everywhere the sorting is happening of our output of our map function. And once the sorting finishes, or as soon as the data is getting outputted, the data is going into 2 buckets. So I'm trying to explain what exactly the magic happening inside merge. Okay, so here itself, some of the keys would go into 1 bucket, other keys would go into the second bucket, and and then while merging, reducer node will have these 3 slots, one dedicated for each map. So first, second, first, second, first, second. So first one will go to the first reducer. This will go to the first reducer. This will go to the first reducer, and second will go to the second reducer. Okay. This way, this way we'll receive first part of each of the node in the here, the first bucket, and second buckets go here. We can merge them, we will merge them on each node individually, and then after merging we will have key and the values. Now the problem is, if we here there is a splitting happening. Some keys are going to one node, some keys are going to another node. Okay, these keys will go to the first reducer, these keys will go to the second reducer. Now in case this partitioning is happening like a random number, so there would be chances that in case, let's say there is a key called apple, and apple went to the first bucket, and apple also came here as the output, and apple went to the second bucket here. In that case, if it goes into second bucket, then one apple would be on this reduce, second reduce, and one apple will be on the first reduce, and therefore it will start becoming a problem. So therefore Hadoop makes sure that while putting the key values onto the buckets, the same key should go to the same bucket. A key, whether on first node or second node, if it's the same, then it'll go to the same bucket. Okay. Now, this splitting is a very tricky process. This splitting is a tricky process. Reason being that if the splitting is not uniform, then you might end up having overloading one reducer over the other. If your function is biased, if Hadoop did not do a good job at deciding this split function, then what might happen is one of the reduced node got all the keys and second one got only few keys. And therefore, one reduced function is overly loaded while other one is less loaded. Okay. Also, it is possible for us to customize this customize this partitioning logic. Okay, we can decide whether one particular key has to go to a reducer, or it has to uh, if one particular key has to go to reducer number 1, or it has to go to the reducer number 2. We can decide that by defining a function called partitioner. Okay, so we can define that using the function called partitioner. So we'll just mention it here. We can also optionally define a function called partitioner. Now, next question from, just increase the font. Next question from Kiran is, if I have 4 nodes and each of the node has 10 blocks, okay, if my file is split size is 4, then where those split store in each node? Okay, if I have 4 nodes and each node has 10 blocks, all right. If my file split size is 4, then where those splits will store in each node? No, I did not get the question. So these 10 blocks do they belong to your file? So do you mean to say that you have 40 blocks? So imagine that your file is having 40 blocks. That's what you're saying. And you have 4 nodes, and these 4 nodes contain 10 blocks each, right? So effectively, total file size is 40. Total file splits are 40. Then, yeah. So those, on each node there will be 10 different files containing your blocks. Okay, on 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 each of these 4 nodes there will be 10 different files containing those your data, and each of them, these 10 files will be of the size of 128 MB each, except for the last block which will be lesser than 128 MB. Okay, okay. So Matthew's question is, data is replicated 3 times, so it would be in 12 nodes. Correct. It might be in 12 nodes. That's another case. Yeah, thank you, Matthew, for reminding me that. So yes. So it will be actually in more nodes than we can imagine, because each data block will be copied onto multiple nodes. All right, all right. So we'll discuss it later. Actually, let I would let Kiran simplify the problem. I mean, simplify the question, and then we can discuss it again. All right, no worries. Now again, so is this clear to everyone? What is happening here? This particular diagram. Feel free to ask if you have any doubt anywhere. All right, all right. So let me repeat it. Let me repeat it here. So you got your input data lying in these blocks. Okay, block number one, block number two, block number two, three. Those blocks will get converted into one line at a time, and that line will go to mapper. Mapper will convert into the key and the values. Why key? Because key will be the basis for all the sorting, and the value is something which you want to bring together for the keys. Now, as a result of mapper, the keys will be broken down into two buckets. First bucket would go to first reducer, second bucket will go to second reducer. If there was four reducers, then there will be these four buckets here on each nodes. Okay, and if there were 10 mappers, then there will be 10 buckets here which need to be merged at each reducer. Okay, all right. And then the data gets carried over. Each set of keys will get carried over to one particular reducer. There they get merged, and for each key, all the values are reduced by our reduce function, and the result is saved into HDFS. All right. Did it make sense, Kiran and Anandita? Okay. So this is the same thing which we have tried to depict over there. Imagine that your data is this. Data got converted into key values by mapper, and then the data got merged here, and then it got reduced. All right, Anandita. All right, should we move ahead? All right, no questions so far. All right, all right. Okay, now again, we can always think of MapReduce as group by. You remember group by? We said select count star from my table group by word. Basically, whatever data is there in this table, we are grouping it by a particular column called word. And then for each word, all the records we are just counting. Okay, we are just counting each record. Now, if you look at this code closely, if you're coming from SQL background, it is basically composed of two parts. One is selection of the key on the basis of which the sorting is going to happen, which is equivalent to our map function, where we are saying that please, this is my call, this is my key, and this is my value, meaning this is the criteria for sorting and grouping, and this is my reduce function. For each of the key, all the values need to be combined using my reduce function. Okay, all right. So is the analogy clear? Do you really think this analogy makes sense, or it's very vague? Correct, Matthew. It's the two ways of doing the same thing. All right, Vaibhav, are you with me? Great, great. So, all right, I'm moving on. If you have any question, feel free to ask. All right. Now, we are going to discuss these problems now. These problems are a little tricky. Some of them are very tricky, and we'll take one case at a time. All right. And these problems, I think, I'll come back to again after some time. The Okay, I think a better thing would be I come back to these problems after I describe remaining things. Okay, let me just go ahead with the session number 3. All right, now demo time. I will try to explain to you one form of how exactly we need to run our MapReduce jobs, and then we will discuss these 4 5 problems. All right. All right. So yeah. So as we told you earlier that when we are launching a Hadoop job, when we are telling Hadoop to execute our MapReduce job, we have to tell Hadoop. So this is something we is common. Okay. That this is my input folder, this is my output folder, this is my mapper, that's my reducer. Okay. Don't get intimidated right now. So there are many ways to get the work done in the form of MapReduce. The most easier one is using a library called streaming jobs. The default one is using your Java code. So you could write MapReduce in Java, but since it's not always possible to code in Java because it takes a long time, it requires compilation, it requires the knowledge of Java. But good news is some people wrote down a library in Java which can utilize any command as mapper and any command as reducer. Okay, as we were telling you that anything that can convert an input into key and value can be your mapper. Any command that can combine values for a key can be the reducer. Okay, therefore, and that is something which you can do using Hadoop streaming. Hadoop streaming is not like handling the video streaming. Okay, it's not, it just sounds like misnomer to me to you. I mean, it's not like YouTube is streaming. It's not like that. It's basically streaming means passing the input streams through the program. Passing the input data through the program is called as streaming. Okay, those who know a little bit about Unix, they would understand that most of the filters do the streaming of the data. Okay, when the data is because data is passed through our Unix filters. All right. So again, so so basically, Hadoop streaming library makes it possible to use any binary or any program as mapper and reducer. Okay. So for example, we are using SED command here to convert our input into mapper and reducer. Okay. The few more things I think I should tell here. All right. Okay. I need to tell few more things here. One is mapper need to gives out key and tab value per line. Okay, and reducer gets ungrouped data having key tab value. Okay, all right, here. All right, let me clear the doubts. All right, okay. So what exactly am I trying to say here? The only difference, in Hadoop streaming and the usual Java MapReduce is that the data which is given to reducer is ungrouped. Okay, reducer doesn't receive the data in the form of group. Okay, the data which reducer would get would be key value, key value, key value, and it won't be grouped like we had discussed earlier. Okay, but all the key values that are fed to the reducer will be sorted. It is just a design that the data to reducer is not grouped, but the data is sorted. Okay, so all right, I think one more step is required here to explain to you what exactly we are talking about. All right. So how many of you are comfortable with Unix commands? Leonid is not comfortable. Okay. Okay. Are you, so all right. All right. So I will try to explain a little bit. I'll try to explain a little bit that will work as a refresher for some of you. Okay. So let me log in to also note that your login passwords are about to get changed. So, okay, let me log into my courses. Okay, so let me just copy it to clipboard. All right. Those who are wondering that how to open the console, we can open the console in the browser. That is something which we did recently. And for you, the login would be Hadoop 16. Hadoop 16. Password we have copied to the clipboard. Now you can see that. Is it visible to everyone? Or should I increase the font? All right. So yeah, before we move forward, so here on this console, this command line, we write the commands like ls is one command which shows the list of files. Okay. And I think I would go to Hadoop 16 at Hadoop1 dot nobigdata.com. All right. Yeah. Oh, there is no file. All right. Or should I log into my own account? So now one more thing, you can see that we can actually switch between Hadoop 1, Hadoop 2 using this way. Okay. Now this is an older account for student. All right. Whenever in this is the Unix command shell. We call it command shell. Here we type the commands like ls. It's giving us the result, and say pwd. It's showing us the present working directory. Using mkdir, we can create our own folder and file. I have already created my own folder called asgiri. It says already exist. I can go into that folder and then ls. Now it will show me the list of files in this folder. Okay. Now, so this is the place where we type commands. Okay. The next beauty, we can almost do everything in Unix from the command line. Okay. We can do everything from Unix from the command line. Okay. Now next thing at Unix is that you can pass the output of one command to another command using pipes. Generally, whenever you type a command or you do anything, the output is visible to the user. Okay. In the same way, you can make the output of one command visible to another command. For example, let's say we want to do let's say we want to do a word count. We want to count how many lines are there. So we are saying ls pipe. This character is called pipe. Okay. This character is called pipe, and we are passing the output of ls to wc. Wc basically counts the number of characters and the words in the input. Okay. Number of characters, lines, and words. So here there are 75 lines, 75 words, and 901 characters. Okay. So the output of ls went to the wc. We can further pass the output of wc to another wc. Now this time there is only one line, three words, and 3 plus 4, 7 plus 3, 10. 10 characters. Okay, how many characters? Yeah, these are more characters actually. One, two, three, four. Each space is counted as character. So you can see that there is one line, three characters, and one line, three words, and 24 characters. Okay. Now even you can pass it further, but the count will remain same because it's again the same thing. Now you can see this, that we are able to pass the output of one program to another program, and we can combine all of this together to form even the very complex things. Okay. For example, let's say we had to do the word count. Okay. Let's say we had to do the word count, so the first thing we need to do is read the file. Okay. Also, before I move forward, there is a command called more. So we are piping the output of ls command, which is giving the list, to more. More will take the input from ls and display it page wise instead of scrolling it all through quickly. Okay, you can see the more at the bottom. Yeah. So basically we are outputting the data of ls to more. Now next step is we need to understand this. How to read a file. Let's say we have got big.txt. Do we have big.txt here? Yes, we have big.txt. We are saying big.txt. When we say cat space big.txt, it is going to read this file and dump it on your screen. Okay, but this file is very big, so we want to pass it to another command called more. Okay, so it's showing page wise to you. All right. Next is that we could also use a command called tail, which basically gives us only the 10 lines out of last 10 lines out of this big.txt, or head, which will give us the first 10 lines of this file. Now let's just take this input. So we are saying just pick up this only 10 lines first. Okay, and then we'll do the word count in this, and once we are successful in doing the word count of only these 10 lines, then we'll switch it to all others. Okay, so we got this input as these a list of lines. Now what we want to do from the command line is want to break this text into into one word per line. The easiest way to do it is replace space, this is space, with new line. So the sed command works like control F. When you press control F in the text editor, you can replace one value with another. In the same way, using sed, you can replace one value with another. Now you can see that the input is broken down into one word per line. Okay, so uh, our first 10 lines of big.txt is printed by head command, that is piped to sed. Sed replaced space with new line, and thus we'll have one word per line as the output of sed. Now we can use a command called sort. You can see that sort has sorted the data. Okay, sort has sorted our input data. Whatever was the output of sed has been sorted by sort command. Next thing we can do is use another command called unique minus c. Unique minus c finds the distinct values, the count of distinct values in the input, provided the input data is already sorted. Okay, now you can see that it has done the counting for us. Okay, and as we told that we can further pass it to sort, and we'll have our results sorted. You can see that the only problem with this is it is not taking into consideration the cases. It is case sensitive. You can see do and do are two different words, so we'll have to do something about it. So we can use another command called tr, which translate one range of characters into another range of characters. Here I'm saying that convert capital A to Z to small a to Z. You can see that everything has been converted into lowercase. Okay, so you can see this. You can also basically try to run each command at once separately, like if you want to test whether this thing works or not, you can take this command and say things like echo. Echo means echo basically. So whatever you want to say, let's say this is your character, you want to convert it into lowercase, so you can convert it to lowercase like this. Okay, so this particular command is converting into lowercase. This particular command is replacing word with, say, let's say we have SA, SAN and GIRI. We can pipe it to SED and it will convert it into one word per line. Okay, now you can see that what we have done here, we have done our word count using these nice little Unix commands. First we printed first 10 lines, then we replaced the space with a new line, that means one word per line. Then we translated the upper caps into lower caps, lower characters, and then we sorted the input data. After sorting the input data, we did the unique. Okay, all right. Yes, minus C in unique gives us the count. If we say don't specify C, it will only give us unique words, not the count. All right, good. So, is this clear to everyone? I'm hoping that I was able to explain. So, feel free to ask me to repeat if there is some portion which you did not understand. This is probably the fastest Unix refresher you can get. You know, I've just rushed through everything really, really fast. So, is this clear to everyone? Okay. Now, I think I have already explained this to this class. Okay. Now, out of this command, which portion is most intensive? Can you tell? Out of these commands, one command, two command, three command, four command, five command. Out of these five commands, okay. So Matthew's question is what happens to punctuation? Right now we are not removing the punctuation. We could actually remove the punctuation. Yeah, using another SED. You will see that quickly in the next discussion. Okay. So here these are the five commands. Which command do you think is most intensive? Correct. So CPU and RAM wise, sort command is most intensive. All right. Now, if we have to do the same thing, we can do the same thing by using SED as the mapper. So this will become our mapper. Okay. And this will become our reducer. Okay. Or we can also say that this will be our mapper. This will be our mapper. Okay. So our mapper will be this, and this will be our reducer. And now then how it will work, we'll explain it, and then we'll do a demo. All right, is everybody with me in this so far? All right, all right, so let me just take a quick break and then come back after the break. Okay, so you can say here. All right, so should we start now? Is everybody back? Should we start now? All right. So, am I audible to everyone? Deepak, Harsh, John, Kiran, Kripa, Leonid, Matthew, Vaibhav. So, all right. So, I think I'm not audible to other persons. All right. All right. Okay. I'm starting anyway. If you have any questions, please feel free to write and please feel free to ask anytime. Okay. All right. So, we were discussing something very, very important, which was Hadoop streaming. So as we told you that you could use any binary or any script to you in as a map reduce. For map or reduce, you could use any script and any program, and that is something done by streaming. Now, question is, in what format should our key and value should be? Should our key and value be for the consumption of mapper and reducer, right? So by default, your program, your mapper program will receive one line at a time in the input from the standard input. The way our filters were receiving the data, the way I just showed you that you could put a pipe and it would read from a standard input instead of reading from you, as in from the screen, from the user, from the keyboard, it will start reading from the another program. In the same way, your mapper program will receive the input from Hadoop in the same format. Now your mapper program is supposed to give out the key and value. The key and the value from the mapper program is separated, should be separated by tab. That is default. But while executing our MapReduce job, we could tell the MapReduce job that my key and values from the mapper are separated by this particular character. Because sometimes your mapper code might be a legacy code which you cannot change. Okay? In those cases, you can tell Hadoop Streaming Library as an option that my key and values are going to be separated by colon or some other character, not tab. Okay, so your again key and value from your mapper by default should be separated by tab. All right, and the the reducer and your reducer will receive as the standard input to the program, it will receive the sorted key value pairs. The sorted key value pairs, and these key value pairs are sorted by the keys. Okay. Now, few more things. Sometimes it's not good enough to just specify sorting. Okay. We might specify that these are numbers and this is lexical. So we can also define and the argument that my key has to be sorted by the in a lexical manner or a numeric manner. If, for example, in case you have 1, 2, and 20, or if you have 1, 20, and 120 and 33, okay, 120 and 3, if you sort them in numeric manner, it will be 1, 3, and 20. But if you sort them in lexical order, this will be the order. So you can tell Hadoop streaming that while sorting, this kind of sorting I want, whether numeric or lexical or some other form of sorting. Okay, so your reducer is supposed to get the data in standard input. All right. And similarly, is mapper is supposed to give out the data to standard output. Now the keys and the values for each key are not grouped, but input is sorted. All right. So eh, I hope the explanation which I'm giving is making sense. Sometimes, sometimes you can choose that your mapper does not give out any values, only the keys. But keys are mandatory. Okay, you can skip out values completely. So let's say you were supposed to give key tab values. Okay, this is key 1, value 1, key 2, value 2. This is how your mapper supposed to give the result. Okay, let me type tab instead of saying this way, like this. Okay, now sometimes you can prefer to skip this. Okay, in those cases value will be considered null and is totally accepted. This is a valid output of the mapper where value is null. Okay, also if you have two tabs, let's say uh, th- this is your input, this is the output of your mapper: key tab, value tab, another value. Okay, in this case, from here till here will be considered value. Anything after the first tab will be considered the other value. Okay, so this is how it happens. So it splits on the first tab. It finds, it doesn't, if it doesn't find the tab, that means everything is a key and value is null. All right, so we'll utilize these properties. So here if you look at it closely, what we have said, we are saying Hadoop jar, Hadoop streaming. This is a syntax where we say tell Hadoop that please execute my streaming job. And these are the input to my streaming job. This is the input folder. This is the output folder. And this is my mapper function, or this is my mapper command. And what does this mapper do? It breaks down the line into key and the value, where the value is null. Okay, it's basically breaking down the whole line into words, one word per line. And we have reducer, which is basically doing nothing but computing the frequency in any input. Okay, now Matthew's question is, since the code is transmitted to the nodes, why is it that any script can be sent, like Java or Python? Yes, anything can be sent. Anything that can execute on that computer can be sent. If you are sending a Python script and Python is not installed on that node, then it will fail. Okay, but if you are sending like Windows binary on Unix, that also will fail. Okay, but any shell command, any Perl script, Python script, anything that can run on individual node can be used as mapper and reducer. Okay, now we have interesting question. Matthew says that so it could use JavaScript provided you can execute JavaScript from command line. Can we execute JavaScript from command line? Yes and no. If we install a Node.js onto every node, then we can utilize Node.js script, which is JavaScript, as the program, as input to, as mapper or reducer. All right. Okay. Moving ahead, let's try to execute this command. Okay. Let's try to execute and then we'll do the dissection. So here I go to my command prompt like here. Also, let me clean up the command. Let me clean up the command. So since it is spread across multiple lines, I'm going to convert it into single line. You can do single line by putting a backslash like this, like this. Now this will become a single line. You can execute it. Okay, let's see what happens. It says that the output directory already exists. Let me delete my output directory. Okay, it's saying that this is already existing. We can delete it from Hue as well as from. Okay, I'm s- okay. You can delete it from Hue as well, but I'm using the Hadoop command line. We can say Hadoop fs rmr means delete a file recursively. Triggering the so Kiran's question is triggering reducer is task tracker job or job tracker. So it's a job of job tracker only. Okay. All right. So we are through with this now. We are going back. Now let's try to execute the command again. Okay, there we go. All right, what does it say? It is telling us that there are total number of two splits, then there are, and it has started. This is the URL to track the job. This is the URL to track the job. You can see that. Yeah, Hue is kind of a UI for Hadoop. That's correct, Matthew. So it says that data node only 1 out of 5 are alive. What's happening to the data nodes? Let me just turn that on. Okay. So what is happening to my program here? Yeah, it has still successfully done it, even though our 3 out of 4 are down. Now our data has been stored at this location. Okay. Also, if you want to see the detailed statistics, as in what's happening, you can go into this and see. All right. So we can see Hadoop fs minus ls as giri slash word count slash output. Alright, you can see that it has saved it here, and let's have a look at what has gone inside. We can say Hadoop fs minus tail and this. Okay, so it has computed the word count and it says that there are 314 pipes. There are 9 times this pipe dot dot has come, and zoology has come only once. Okay, you can see that. Now there are few things like there are these special characters, there is capitalization, so we might have to solve these problem in our input. Okay, therefore, alright, those who are wondering what's happening inside, I think this diagram will make it clear. So the input line, each input line is given to SED. SED converts it into this, and then this the Hadoop basically is sorting it. Hadoop is sorting the data, and then unique is just computing the word count. Okay, so Hadoop's role is just this sorting of the data and uh, reading the file and giving it to SED. Okay, all right. Had there been multiple reducers like this, what would happen? Okay, here again, these key values, whatever we have generated as part of our mapper, will be split onto multiple machines. Just that same key will always go to the same node. One key cannot go on to multiple nodes. All right. Now let's say we want to clean our data further. Okay. Let's say we realize that after SED, what we want to do is we want to replace we want to remove everything which is not A to Z or 0 to 9. We replace it with nothing. Similarly, we are saying whether it's a space or tab or any number of these, we replace it with new line. Also, we are translating the capital into lower. That's what we are doing. So whatever input is coming to this bash script, it will get converted into one word per line, as well as every special characters will be removed, and then the capitals will be converted into lower cases. Okay, so that's what is going to happen when we execute this script. For each input, these are the things it is going to do. Okay, now here we are also, there is another thing we should note is we can specify how many reduced tasks we want in the output. Okay, we can tell that we want 2 or 3 or how many. Okay, so we have input folder, output folder. We this time, instead of only providing one command, we are writing it into a file called mycmd.sh. Okay, so I must have done it must be there in my folder. Okay, is it there? MyCMD, yeah. And let's see what is there inside it. So you can see that what we are doing here is we are executing all of this. And there is one more special thing we are doing. Now, since this command called mycmd.sh does not exist all on all the data nodes, we will have to ship it. Correct? In the previous example, we used only two commands. One was SED and other was unique. And both of these commands already exist on all my nodes. Correct? Because they SED and unique are part of the basic OS. Therefore, SED and Unix were available already. Now, in our case, we have done some customization, and we have written this script. Now, this script we try to execute. If we try to execute this script on Hadoop 2, Hadoop 3, Hadoop 4, it may not exist there already. Therefore, it's very important to understand that we need to ship it. And how does that work in case of MapReduce? When we ship something to the node, it basically copies that script to a temporary folder, and in that temporary folder it will execute Hadoop MapReduce job. Okay, so whenever we pass some data or pass some file, it copies that data or that file into a temporary folder and execute it from there. Okay, because it's very important to understand that mycmd.sh will have to be executed at might it might get executed on 4 different machines. Therefore, this mycmd.sh need to be shipped. Also, we come to the conclusion here. Let's say we are writing a Python program, and your Python program requires certain modules in Python, and those modules are not installed on your cluster. In those cases, your program will fail. Therefore, your Python modules need to stay updated on all the nodes. Same is the case with any other programming language. Okay, so again, the way we are shipping mycmd.sh, if we were depending on any other program. So let's say my library.sh, we had created this separate command which we wanted to use in my CMD. We could also ship that one. We could also ship that one. Any questions here? So let's say we just pick it. All right. Again, we are just putting backslash it just to avoid the new line because the command is spread across multiple lines. Either I remove the multiple lines or I do this. Also, please note these special quotes. They bother me a lot. Okay. Now let's try to execute it. Let's try to execute it. So it is saying that, all right. So we are saying Hadoop jar, my streaming.jar, input is this, output is that, and mapper is here. Do you see any mistake in this? So output folder already exists, that we can say 25 July 15, and now we can also understand why exactly this particular argument is failing. Yeah, it has to be file. Okay. Although it says that that is deprecated, but it isn't. It is not deprecated. All right. Now you can see that it is going to execute it now here. All right. Any questions here? Okay. So Krupa says that what does D option do? D option basically specify a variable. In case of Java program, we use -d and then provide the variable name. Here we are saying my MapReduce tasks need to be 2 this time, not 1. Okay, our reduce task, not MapReduce. Okay, so yeah, we found the problem, and yes, now it has finished the work and the output is in this folder. We can see Hadoop fs -ls. This time there should be two folders, two files inside this folder. You can see that one is part 0, other is part 1. So you can say Hadoop fs -cat. Now you can see that this time it is far more cleaner. This time it's far more cleaner. You could also say things like star, and we could say sort by numeric and do the more. So whatever is the output of all the parts, we can further sort it and then see the result. Now the has come 80,000 times in this text. So now you can guess that it's a English, definitely an English text, and it's a not a code. You can see all of that. Okay, so this word frequency analysis is very important. So we were able to clean it and solve it. So is that clear to everyone? So this is how you could write any script, your custom script, to get the map reduce done. To get the map reduce done. Okay. All right. Now next step is that it is okay to have no reducer. We may choose not to have any reducer at all. In those cases, the result of mapper will not be reduced. As in, multiple values will not be combined together if there is no reducer. Okay, so if there is no reducer, the command will not have minus reducer. This command will not have this particular line. Okay, also you can turn off, you can tell Hadoop that we do not require sorting in our problem. Do not sort my key values, let it be the way it is. Okay, specifically if you are translating the input data from one form to another, then you generally don't require the the reducer phase. You can just turn off the total number of reduced tasks to 0 and it will not do the sorting for you. Okay, now you might ask that how many mappers and how many reducers should be there. Number of mappers is basically a function of how many blocks of file do you have, or we call them input split. We'll talk about difference between block and input split later. But right now you can think of input split as equivalent of a file block. So number of file blocks decide and dictate the by default, that is the only reason, the only logic behind shipping the mapper to multiple nodes. You can, though you can change that by setting the config, and in the config you can set that number of map tasks are these many. Okay, the number of reducers is a little tricky part, and it's always ever going discussion on how many reducers need to be there. Okay, as a thumb rule, you first compute what is the ability of your cluster. How many tasks can your cluster execute simultaneously? Okay, if you have two machines only, first machine can execute two tasks and second machine can execute three tasks. This three or two is something is configured by you again, and and you generally make sure that if you have more number of processors, you define more number of tasks on each machines. Okay, so number of tasks on each machines you decide based on the ability of your machine. Okay, and then you count the total number of tasks. Then you count the total number of tasks that become your maximum possible tasks that could be executed in your cluster. Okay, and 0.95 times of the maximum task to 1.75 times the maximum task is something you need to choose between. Between these two ends, you need to choose your number of reducers. The minimum number of reducer you should choose is generally 0.95 times the max number of reducers. and the maximum number of reducers you should choose is 1.75 times the max reducer. So if you have, say, total number of tasks at 100, if you have, say, 10 machines and each machine has got ability to execute 10 tasks, therefore there will be total possible tasks at any point of time would be 100. And in those cases, total number of reducer you should choose is between 195, sorry, between 95 to 175. Okay. So so if you have more number of reducers, it might sound like you have solved your problem, but but sometimes it might also slow you down, because if you have smaller data and you are using more reducers, the 90% of the time will go into shuffling of the data, and that's not a great thing. I- if you have more number of reducer, meaning more number of shuffling and hence network load, and therefore it it becomes very slow. But if you have very small number of reducers, if you have one reducer or two reducer, the overall load on a single node could be very high, and therefore also also if one reducer fails, then the whole process will start from the beginning, right? The same process will be started on another node. But in case you have 20 reducer and one of the reducers fail, only that particular process need to be executed again. Okay, therefore the lower chances of failure are there if there are a smaller number of reducers. Okay. There if you have a smaller number of reducers, therefore there are higher chance of failure. Okay. Uh, and but in case of a smaller number of reducers, the overall overall network load on the cluster, because shuffling is going to be very less if there are low number of reducers. Okay, so is it clear to everyone? All right, so you generally, to be honest with you, given these two limits, given these two extremes, you generally do a hit and trial. You first on day one, you try to execute. On day one, you try to execute 95. On day two, you try to execute 175 reducers, and then you try in between, and you keep trying unless you get the best number. All right. Any questions here? Do we have any questions on this? No questions. No. All right. All right. Seems to be no question. Okay, now going back to the problem, we'll discuss one problem at a time. Okay, and all of you need to, participate in this. Okay, so the frequency of letters from A to Z, do you need MapReduce? For computation of frequencies of letter from A to Z, if you want to compute the frequencies of letter in a big text file, do you think we require MapReduce? Matthew says yes. Anybody else? Vaibhav says yes. And why? So if you have 1 MB file for which you have to do the computation of frequencies of letter, will you use MapReduce? Matthew says that the letter is the key and the frequency will be the value. Correct. Webber says that even though the hash table will be limited to 26, MapReduce makes sense if the file is in gigabytes or more. Very good. Very good. Anybody else? Yes. And for a small file, not correct. Anybody else? Any other answers? So, do you think we require MapReduce to do the frequency analysis of a file which is of say few MBs? Do you think do we need MapReduce? Yeah. Yes. Correct. We do not require the MapReduce in case the file is smaller. Here the problem is not CPU or RAM, because counting the characters is very easy. As Matthew is saying, that you can actually use the fingers to count, as in you just need to keep track of 26 numbers, right? You can keep track of these 26 numbers, and that will make it possible to basically count the characters in a very small RAM using a very small CPU at a time. The only problem occurs when your data is in, say, above 15 gigabytes. Okay, the if the file is of more than 50 gigabytes, what would happen is that the IOs will take maximum amount of time. The disk IO will take maximum amount of processing power, and therefore is not well is not well suited for single machine. Okay. Without MR approach, we could basically create an array of 26 characters and then count the frequency of each characters. All right. The network IO will be the bottleneck, and in case the file grows bigger, apart from network IO or the disk IO, the CPU will become the bottleneck. Okay. Using the map reduce approach, we could basically count the number of characters in the file using making the letter as the key and number of occurrence of that particular letter in each line as the value, and that we can do on each of the mappers. Okay, and once that is done, in the reducer we can just sum it up. All right, the approach is very similar to the character count. Okay, the approach is very similar to the word count in the approach in character count. So does anybody has any other approach? So let me just list it down. So first approach is the key is each character and the value is and the value is 1. And this is our first approach. In the mapper, this is what we are doing. Okay? In the reducer, in the reducer, we are basically just summing. Okay? We are just summing the values. Alright? The another approach could be any other approach in this? In character counting, do you have any other suggestions? If you have to do the map reduce, do you have any other suggestions? Alright. You could also do things like in mapper, for each line count the characters and print the statistics. Okay, such that a key is a character. Key is a character, and the value is number of occurrences of a character in that line. Okay, like this. Okay, and reducer remains same. Any other approach? Can anybody suggest? All right. So come up with your own ideas on this one. These are my ideas. Okay. Come up with your own solutions and write the pseudocode or use the Hadoop streaming to solve this particular problem. Have a look at and submit it in the assignment itself. Here you see the subjective question assignment. There you can submit your answers. Okay. Okay. Here you can submit. Also you will have here if you want to see what have you submitted already, you can go to user account and click on my results. Okay. You will see this. Also, any quiz you take, we keep a record of the whole history, but you should always attempt it multiple times. Okay. In case you are, you can, basically you can attempt any quiz any number of times you want. Okay. All right. Good. Good. So next question to all of you is find the anagrams in the Hughes text. An anagram is basically a different arrangement of letters in a word. How can you use MapReduce in the same way? Alright, before going with that, there is a question from Matthew that aren't these two approaches same? This one, second one is little more optimized because we are reducing total number of keys by for each line. If there are duplicates, we are not counting them twice. We are just keeping one key for them. Okay, so the total number of keys will be lesser in this. All right. So who has done this one? Who has thought about this one? Question is you have to find the anagrams in a Hughes text. Okay? An anagram is basically different arrangement of letters in a word. So the cat act in tic-tac-toe. The has no anagrams in this text, while cat act and tack is anagram are anagrams because they are basically different arrangements of the same letters. Same letters as in C, A, and T are the three letters out of which we have formed, out of which if you rearrange these letters, you will get tack and cat. So you have to find the anagrams using MapReduce. So what exactly are you going to do? What should be the key such that all the anagrams for a word should come together? What is the key that is same for all anagrams of a word? No matter what is the word, if it's anagram, it should have the same key. So what is the common thing about in cat, tack, and act? What should be the key? Because as we have already told in MapReduce, all the values of a key would come together because we sort the data based on the key. Therefore, therefore, can you come up with a logic for forming the keys such that all the anagrams should come together? So Kiran says that in Java I can check the ASCII value for each character in the word. Okay. If it is same, then those words are anagram. That is correct. If we have to do that, we can basically go from one end to another. But then again, it will have the same problems as word count, right? If you have a text file of say 50 GB and you have to find the anagrams in that 50 GB, then doing it in a traditional way where we are reading the file, going from left to right, forming a hash table and getting it done, it will be really, really intensive. All right. Okay. Matthew says that you can create a hash for key and value, and we can compare each word for same letters. So what will be the key in the hash table, Matthew? Okay, so he says that each key has to be the set of letters. Nice, keep going, yes. On the similar line, can you think about MapReduce? What should be the key that is that would bring all the anagrams together? Okay, Vaibhav says assign numbers to each character. A is 1, B is 2, and so on. Okay, and then do similar to the map reduce of word count. Okay, so if we assign the numbers, right? So what will happen? Cat and say BBT will have the same count, right? No. So let's say what he's saying 3, 1, and some number, right? So T is what? T is TUVW. T is say 21, right? Is equivalent of say we have CABA, right? That is also this one. Okay, but you are on a very similar path. Vaibhav continues that, but when the value of the word matches a key, add to the value. Okay. If key is sum of the values in a word, then there is another problem. Then cat and BBT will have the same value, isn't it? If we assign one number to each one, cat and BBT would have the same sum. Okay, now let me go with the answer which Leonid has given. Keys should be sorted character list of each word. Brilliant, brilliant. He says that for for let me just copy his answer. Say for example, for the it is EHT, for cat it is ACT, for act it is act, for in it is in, and for TIC brilliant, brilliant. That is one of the answers. All right, brilliant. All right. So, Kiran, even if we do the ASCII values instead of normal ways, still the problem would be the same, right? So, ASCII value summation may not work. You try doing the ASCII value summation, cat and BBT would result in the same value. Okay. Now, Anandita says that store the values in a hash table for each letter. Okay. So, Anandita, okay, okay. And then sorted. Store the values in a hash table for each letter. So, what is the key in the hash table? That's what I'm interested in, Anandita. So, what will be the key and what will be the value for hash table? Yeah. Okay. 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 That's also a good approach, I would say. Okay, so what Anandita is saying that let's say there is cat, we could store it after sorting. We could say A1, C1, T1. Is that what you're hinting at, Anandita? And if it is say school, then S followed by 1, sorry, it'll be C 1 H1, okay, L, then L1 O, 2 S1, right? Is that what you're saying, Anandita? Yes, that's also correct. That's also correct. All right. So, okay, any other suggestions? I actually from other classes I have some more suggestions, but I'll not confuse you. I'm looking forward to your solutions. We basically have to form a key such that we can tell MapReduce that hey, this is my key, bring all the values together, and it would bring all the rearrangement of our letters in a word, all the rearrangements together, meaning all the anagrams together. Okay? Yes. Yes. Okay. Correct, Weber. So yes. So the only thing is in whether in this case the one which we have discussed from Anandita, what we have to do is we have to put the value as the actual word and key as our key. That way we'll not lose our actual value. Yes, that's correct, Matthew. So I think all of us are agreeing for this kind of a solution. Ouch, what happened to my presentation? Okay, all right. So now let's have a look at this one. Good. Now you can see that. So what we are doing here is in this approach. This approach is the approach from Matthew and Leonard, and similar to what Anandita has suggested. So basically, we sort the letters of each word alphabetically. That becomes our key, and the actual word remains the value. All right. So now you can see clearly that for cat, act, and tech, the key is ACT. Okay. And then, so basically we sorted the characters in the word, and then that becomes the key. Value remains the actual word, and this dashed line is what is being done by Hadoop for you. Okay, it sorted the words by the keys, and then you either if you're using Java MapReduce, then Hadoop will group it for you. Otherwise you can group it by yourself. It's not a big deal. You can go from top to bottom. As soon as the key changes, you append the values. You basically print the keys. Okay. So grouping is not a big deal. Grouping is very straightforward. You keep on going from top to bottom. As soon as the key changes, you consider it as a new key. Otherwise, you keep on appending all the values together. Okay. Okay. And reducer does nothing in this game. Reducer does nothing. It basically prints out the distinct keys. All right. Now, now So Leonid is saying that would it not be more effective for reducer to perform concatenation? Yeah, reducer has to inevitably perform the concatenation. Okay, it's just the grouping we were talking about. All right. Now I hope that was clear to everyone. Was it clear to everyone? Yeah, you mean this one? No, this is not concatenation. It is just grouping. This might be an array of values. Okay, concatenation is being done by the reducer. It just looks like that's the way I could represent it here. All right. So, okay, so is it clear to only Matthew or everybody is on the same page? Okay, so it's clear to Leonid, Matthew, Vaibhav, and Kiran. Rest, is everybody clear about this? All right, great, great. Okay, now let's move on to the next problem. Next problem is this is probably quite easy. You have, say, DNAs of the people in a file. This file contains DNA such that in the following format, each line contains user space DNA. And what you need to do is you need to find out the people with the same DNA. Okay? You have to find out the people with the same DNA. What will you do? Anyone? Okay. Kiran is saying let the DNA be the key. And Leonid is saying mapper should reverse the order and create name value. Okay. Similar approach as last time. Okay. Here we are just trying to find out the people with the same identical DNA. Okay. Brilliant. Brilliant. Weber is saying if the file is really huge, then use the MapReduce. Otherwise, use SQL. Good. And okay. Okay. Brilliant. All right. So basically, we are trying to group people. We want to bring all the people together whose DNA is identical. It's probably very straightforward. So, Matthew, we do not want to bring user 6 and user 1 together. Mind that. Okay? We do not want to bring user 1 and user 6 together. Correct. So what we want to do is user 1 and user 4 who are ACGT, we want to bring them together. Probably you are thinking about the next problem because you have gone through the problem set, you're thinking about the next problem. Yeah, correct. You are actually thinking about the next problem. All right, let me, okay. So the answer here is very straightforward. The key will be the DNA and the value will be the user. So which is very straightforward. Does anybody need explanation? I can explain it further. Should I explain? Okay. So in this case, in this example, okay, here, ouch. All right, here, like this. Let me just, okay. All right, now it's cleaned. So if we form the, what we want to do is we want to bring user 1 and user 4 together. Okay. Similarly, we want to bring user 3 and user 5 together and user 2. Why? Because they have the identical DNA. Okay. So what we need to do is we basically need to bring the keys such that for for this one this will be the key and this will be the value. Okay, this will be the value. Similarly, for this one, this will be the key and this will be the value. Okay. Or I could do a little clever thing. I could use a regular expression like this. Okay. And I could say $2 tab $1. Have you guys gone through the regular expression video? So now you can see that it is tab separated key value. Now if I sort it, then user 3 and user 5 has come together, user 4 and user 1 has come together, and user 6 and user 2 are separate. All right, good, good. Anandita, is that clear now? Great, great. So this one should be clear to everyone. If it is not, then please let me know immediately. Deepak, great. Moving on. So this one is clear to everyone. Now here is the tough one. A tough one. Let me see who all can solve this one. Okay, it's not that difficult. I'm just trying to. Out of all of these 3 4 problems, this is probably a little difficult than the others. So the problem statement is that if you have got key value pairs of username and DNA, you have got users with their DNA. Now, some researchers have told you that all those people whose DNA is either the mirror image of each other or is exactly identical to each other belong to the same family. Now, you have to bring the family together. Okay, so you're given a huge list of DNA and you are told that the people who has either identical DNA, for example, user 1, user 2 and user 4, which is ACGT, ACGT and TGCA. ACGT, TGCA. TGCA is just mirror image of ACGT if you read it from backwards. TGCA and user 4, which is ACGT. So user 1, user 2 and user 4 either have identical DNA or mirror image. Similarly, user 3 and user 5 have exactly identical DNA. They have identical DNA and that's why they are together. And then user 6 has nobody in that family. Now you have to group these users such that their DNA is either identical or the reverse of each other. So how would you do that? Okay, so above says same as previous one, but if DNA is mirror, don't create the new key. Okay, so how do you identify that it is a mirror? So Kiran says the key will be DNA in sorted order. For user 1, he is saying that ACGT, and user 2 it will be ACGT. Okay, user 4 ACGT. But imagine this, user number 4, right? User 4 and user 1 will get grouped together. Sorry, user 6 and user 1 and user 2 and user 4 will get grouped together. That's what we don't want. User 6 does not belong to the same family as user 1. From Karan's logic, where we are sorting the characters, that will happen, right? If we try to do it like anagram, then user 6 might go in the same group as user 1 and user 2 and user 4. Okay, okay. So Vaibhav, try to give me an example. I think you are on a very right track. Okay, so mirror image means if you read it backwards, then it should match. Say ACGT, and if you see this one, it's basically just exactly opposite of user one, right? That's a mirror image. You read it from backwards. While sixth one is not that way, right? Sixth one GC is in a different manner. Okay. So see ACGT and user 2 is exactly opposite like TGCA. But sixth is neither the same as ACGT nor is the mirror image. Kiran, did it make sense? Mirror as in exactly reverse of it. And okay, Matthew says create a key variable equal to the DNA sequence, okay, or the reverse. Okay, okay, this is good. You're going in the right direction. Okay. Good. Good. Okay. Good. Good. Now Matthew says if variable equal to ACGT or variable equal to TGCA. Interesting. So please note that at a time you will be only having one line to process. In your map function, you will only get one line, as in one user and its value, its DNA. Only that will be the input to your program. You have to take a decision only based on that. All right. Okay, so we'll take a break here. You think about this problem and we will discuss it again. It's good that we got some break in between. So you think about this problem and we come back to this problem again tomorrow. Okay, try solving all the four problems. It's not that difficult as it sounds. Okay, try to solve it and then we have the discussion again tomorrow. All right, sounds good to you? All right. Leonid's question is how proficient with Java Unix do you have to be for capstone project? To be honest with you, I have not worked on a capstone project so far. Okay. I will have to take a look at what exactly does capstone mean. All right. Okay, then we will see you tomorrow. Okay. Okay, the project which we will discuss then, you don't have to be too proficient with any of this. The project we are going to discuss in the end, there will be two projects. One is with respect to recommendation, other is with respect to the sentiment analysis. Sentiment analysis has to do more with the SQL. Okay, and while the recommendation project might require a little bit understanding of Unix commands, and if you were able to understand the Hadoop streaming example we gave, you would be good to go. Okay, you'll be able to do that. All right, great. See you tomorrow. Bye bye. Have a great day. Thank you, Leonid. Thank you, Kirpa. Thank you, Vaibhav. Have a great day, and see you. See you tomorrow.